In this problem, we're trying to roll a wheel up an incline by wrapping a band around the wheel. One end of the band is attached to a fixed wall there at A. There's a constant force F applied at the other end, where it's coming off the top there at some point which I'll call B. The wheel does not slip, so we'll see that C here is the instant center for the wheel. Then as a result of this applied force F and the fact that the wheel starts out from rest, what we want to do is find the speed of G after G has moved up the incline a distance of 0.8 feet. The free body diagram we're going to be drawing is going to be one which helps us with the work energy equation, because we're looking for change in speed for change in position. So the goal here is to use the free body diagram to figure out which forces, if any, do work. So there's the applied force F here at point B. There's a normal force at the bottom. There's a tension force down here at the bottom that is required to help hold the wheel in place. But it doesn't do work, because it acts at the no-slip point there at C. Normal force, the same thing. It doesn't do work. The weight force, which is there, and it does work, but we're going to put that in V. The only force that we have acting, which does non-conservative work, is the applied force F. So for the work energy equation, we say that the kinetic energy at the beginning is a 0. The problem says initially at rest. V1, I'm going to put the datum at the beginning position. That's my choice. T2 is equal to 1/2 mv squared plus 1/2 mass moment of inertia about g omega squared. If we use G as our reference point, might be better in this case to use C as a reference point, because C is a no-slip point, 0 velocity. So we can shorten that from 2 terms down to 1, where the mass moment of inertia we need to use for C is what is for G plus mr squared. This is the parallel axis theorem. And since Ig is 1/2 mr squared, this becomes a 3/2 mr squared. V2. The datum was chosen at the beginning state, so it's going to be moving up from there. mg times the distance through which G moves up the incline. They actually change in height, though, goes as the sine of the angle. The work done by that force F, by definition, is we take the force as a vector, we project it onto ET, we integrate it over to the path of the point of application, which is B. Well, since F is aligned with the direction of motion for B, and since F is a constant, we can move that on the outside. So this becomes the applied force F times the distance through which B moves. Note that there's a difference between delta SB and delta SG. G is how far B moves. SB is how far B moves. We need to be able to relate those two. The kinematics. The kinematics are really based on the fact that C is the instant center. It doesn't slip. So what that says is that the speed of G is going to be equal to r omega. That makes sense. The distance from C to G is r, and we know that the speed of any point is a distance back to the instant center times the omega. By the same argument, VB is equal to 2r omega. B is a distance of 2r from C. So we have this. So from this we see that VB is equal to twice VG. The top point moves twice as fast as the midpoint. And if we integrate this over time, we get that delta SB then is equal to 2 delta SG. We are now in a position to solve. We're going to have one equation for one unknown. The initial kinetic, initial potential, the work, is F times delta SB, which is 2 delta SG. And that's equal to 1/2. IC we saw was 3/2 mr squared times omega squared. And then the potential was equal to plus mg delta SG times sine of theta. So from that, we can solve for omega. And knowing again that C is the instant center, we can say that the speed of G then is equal to R omega, and we've got that answer there. What we did here was use the work energy equation. A very key part of this was for recognizing that as the wheel rolled, it didn't slip at the contact point there of C. So we referenced that point when we wrote down our kinetic energy expression. We wrote down the potential. We found the work. The work was equal to the applied force times the distance through which the top piece of that band moved. And finally, in the kinematics, we proved that the end of that band moves twice as far as the center of the wheel moves. Putting all those together, we solved the work energy equation, and we ended up with our answer there for VG.